The story of Max Planck begins in the quiet city of Kiel, Germany, in the late 19th century, a time when physics was believed to be complete. Scientists around the world were confident that the universe had revealed nearly all its secrets. The laws of Newton described the motion of planets and falling apples, while the equations of Maxwell captured the essence of light, electricity, and magnetism. It was said that all that remained for physics was to measure everything more precisely, to fill in the last few decimal points of knowledge. But amidst this calm certainty, a storm was quietly forming, one that would eventually reshape the very foundations of science. And at the center of that storm stood Max Planck. Planck was not a man of rebellion or revolution. He was a man of logic, patience, and deep moral conviction. Born in 1858 to a family of scholars, he grew up surrounded by music, mathematics, and faith. He saw science not as a tool for fame, but as a way to uncover the hidden harmony of nature. A harmony he believed was rooted in order and reason. When he entered the University of Munich, he didn't dream of overturning classical physics. In fact, he admired it deeply. His early teachers told him that there was nothing new to discover in physics, only refinements. Planck accepted this at first. He didn't want to chase mysteries, he wanted to perfect understanding. But as he began to explore the laws of thermodynamics, the science of heat, energy, and motion, he found himself drawn toward one of the most puzzling problems of the age: blackbody radiation. A blackbody, in simple terms, is a perfect absorber and emitter of radiation. Imagine heating a piece of metal in a furnace. As it grows hotter, its color shifts from dull red to bright orange to white, and eventually to a bluish hue if heated enough. This transformation of color with temperature fascinated physicists. It was more than just a visual change. It was a fundamental clue to how energy is distributed in the universe. Scientists wanted to understand how much energy was radiated at each wavelength as an object heated up. But when they tried to explain it using classical physics, the results were absurd. In laboratories across Europe, experiments were conducted with great precision. Using furnaces lined with soot, scientists created near-perfect blackbodies and measured the intensity of the radiation they emitted at different wavelengths. The data was clear and consistent, but the theories, the equations derived from the well-established laws of physics, could not fit the data. When plotted, the predictions of classical theory exploded into infinity at shorter wavelengths, suggesting that a hot object should emit an infinite amount of ultraviolet energy. This absurd result was mockingly called the ultraviolet catastrophe. It was a disaster for physics, an open wound in what was supposed to be a perfect body of knowledge. For Max Planck, this problem became an obsession. He was not seeking fame or recognition, he was seeking truth. The blackbody problem was not just a technical challenge, it was a philosophical one. It questioned the very structure of nature's laws. Why did the equations fail? What was missing in the beautiful logic of classical physics? Planck spent long nights in his study, surrounded by sheets of calculations, scratching through equations by candlelight. He tried every approach he could imagine, using the laws of electromagnetism, thermodynamics, and statistical mechanics. But every attempt brought him back to the same impasse. For years, Planck worked in solitude. He was known to his students and colleagues as a man of quiet discipline, polite but distant, completely absorbed in his thoughts. He rarely spoke of his frustration, but those close to him sensed his unease. He once confessed that he would give anything, even his life, to know the true nature of radiation. The problem haunted him. Day after day, he compared theory to experiment, hoping for a hint of reconciliation. None came. Classical physics insisted that energy was continuous, that it could be divided infinitely into smaller and smaller parts. But the universe seemed to disagree. Something about the way matter emitted and absorbed light defied that logic. The late 1890s were a time of both discovery and confusion in physics. X-rays had just been discovered by Wilhelm Röntgen, and mysterious particles called electrons had been identified by J.J. Thomson. The world of the atom was beginning to reveal its secrets, but no one yet understood what held these strange findings together. Amid this growing uncertainty, Planck remained focused on his blackbody problem. He did not know it yet, but he was standing at the edge of a revolution. In 1899, Planck developed an equation that fit the experimental data almost perfectly. But it was purely empirical. It worked, but he didn't know why. That was not enough for him. Planck was not satisfied with formulas that merely fit the numbers. He wanted a deeper, physical explanation. He turned to the work of Ludwig Boltzmann, a brilliant but controversial physicist who had developed the theory of statistical mechanics. The idea that heat and energy could be understood as the motion and behavior of countless microscopic particles. Many of Planck's peers distrusted Boltzmann's ideas, seeing them as too abstract, too philosophical. But Planck, desperate for insight, decided to explore them. Boltzmann's equations described how energy could be distributed among atoms in a system, and they relied on probability, the mathematics of chance. Planck was uncomfortable with this approach. He believed nature was governed by absolute laws, not randomness. But as he studied Boltzmann's work, he saw a faint light in the darkness. If energy was not continuous but came in small, discrete chunks, perhaps the statistical behavior of radiation could finally make sense. With great hesitation, he decided to make an assumption, one that went against everything he believed. He proposed that the energy of light was not spread evenly, but released in packets, or quanta, each proportional to the frequency of the radiation. This was not a eureka moment of triumph. It was a moment of quiet resignation, a last resort by a man who had run out of options. Planck himself later said that he introduced the idea as an act of desperation. He did not believe it represented physical reality. It was simply a mathematical trick to make the equations work. But when he tested his new formula, something extraordinary happened. The results matched the experimental data perfectly, across every wavelength, every temperature. The puzzle fit. For the first time, scientists had a theory that described the full curve of blackbody radiation, from the infrared to the ultraviolet. Planck's formula worked with stunning accuracy, and when he presented it to the German Physical Society on December 14, 1900, it marked the birth of quantum theory. Yet, the audience barely realized it. There was no applause, no declaration of revolution. Planck's discovery entered the world quietly, like a whisper in the noise of scientific progress. Even he did not grasp its true significance. But beneath that calm surface, the universe had shifted. Planck's assumption that energy was quantized broke the smooth, continuous fabric of classical physics. It introduced a new vision of reality, one that would soon transform everything from atomic structure to the nature of light. Planck had touched a secret that would later explode into one of the greatest revolutions in human thought. Still, in those early years, the struggle was not over. Planck was deeply uneasy with his own idea. He was a man of certainty, and the quantum, with its discontinuities and strange behavior, felt alien to him. He spent years trying to reinterpret his theory within the framework of classical physics, hoping to find a way back to continuity. But the universe refused to yield. Other scientists began to take notice, among them a young Albert Einstein, who would soon build on Planck's concept to explain the photoelectric effect, proving that light itself behaved as particles called photons. In those early moments, before the quantum world had a name, Planck stood alone. A man divided between tradition and innovation, reason and mystery. His journey was not that of a triumphant genius, but of a reluctant pioneer, pulled by truth into unknown territory. The blackbody problem, once a minor technical issue, had become the doorway to a new physics, one that would soon redefine energy, matter, and even reality itself. Planck's early struggle was a testament to the quiet endurance of a scientist who refused to give up, even when his own beliefs stood in his way. He had no intention of changing the world, yet he did. In his long nights of calculation, amidst frustration and doubt, he had discovered a principle that would reshape the entire scientific landscape. The road to quantum theory began not with a grand experiment or a public announcement, but with one man, a stubborn problem, and the courage to question what everyone else accepted as truth. And as Planck looked upon his final equations, he could not have known that this reluctant step, this act of desperation, would one day inspire the greatest minds of the 20th century and lead humanity into an age of technology and understanding beyond imagination. As the new century dawned, Max Planck's quiet discovery lingered like a seed waiting for light. In 1900, Europe stood on the brink of transformation. Electricity was reshaping cities, telegraphs carried voices across oceans, and science was admired as the engine of human progress. Yet in lecture halls and laboratories, the most disciplined minds still clung to the comfort of continuity. They believed that nature was smooth, predictable, governed by the steady curves of calculus. The idea that energy could leap in discrete packets seemed almost heretical. But slowly, like ripples spreading across still water, Planck's strange assumption began to reach curious ears. In Berlin, Planck himself remained calm, almost indifferent to fame. He continued teaching, publishing, and refining his calculations. To him, the Blackbody equation was an elegant solution, nothing more. But beneath his modesty was a quiet uncertainty. He sensed that his formula carried a hidden message he could not yet decipher. Students who attended his lectures recalled his voice, soft, deliberate, almost musical, explaining with mathematical precision how the radiation curve could be derived. Few realized that they were listening to the beginning of a new era. Meanwhile, a young physicist working in a patent office in Switzerland was reading Planck's papers with intense fascination. Albert Einstein saw in them something revolutionary. Where Planck had used the quantum as a mathematical trick, Einstein saw a physical truth. He argued that light itself was made of these quanta, that energy came in lumps, later called photons. To the scientific establishment, this sounded absurd. For centuries, light had been known as a wave, but Einstein's bold leap was inspired entirely by Planck's equation. It was as if the older scientist had handed him a key without realizing it. When Einstein published his paper on the photoelectric effect in 1905, he cited Planck's constant, the mysterious number that defined the size of a quantum, as the foundation. Without Planck, there would have been no quantum theory, no relativity, no modern physics. Yet at that moment, the world still saw Planck as a conservative scholar, not a revolutionary. He himself continued to question what his discovery truly meant. For Planck, the struggle was deeply personal. He was a man rooted in tradition, shaped by the moral and intellectual discipline of 19th century Germany. To him, science was not just about equations, it was about truth, unity, and faith in order. The notion of randomness, discontinuity, or indeterminacy made him uneasy. When younger scientists like Einstein and Niels Bohr began to push his ideas further, suggesting that the universe itself was probabilistic, Planck resisted. He could accept quanta as a useful concept, but not as a reflection of nature's ultimate reality. The early decades of the 20th century were filled with debate. Planck watched as his reluctant hypothesis blossomed into a movement that defied everything he cherished about certainty. The old guard of physics, those who had built their careers on classical laws, struggled to accept it. But experiment after experiment confirmed the quantum behavior of light and matter. The ultraviolet catastrophe was gone, replaced by a new vision of the microscopic world. In the laboratories of Europe, young scientists began exploring the mysteries of atoms and radiation using Planck's constant as their compass. Each discovery, the quantum jump, the wave-particle duality, the discrete atomic spectra, carried the fingerprint of Planck's insight. In public, he appeared calm and composed, even when challenged by peers who accused him of abandoning realism. Privately, his letters reveal a man torn between logic and belief. He once wrote, "I did not seek revolution, but I could not deny the results." This simple confession captures the essence of his struggle. He was the first to pierce the veil, but he could not bear to look fully beyond it. Outside the world of physics, Europe was changing in darker ways. The First World War erupted in 1914, and Planck, then in his mid-50s, saw his country descend into chaos. Like many intellectuals of his time, he felt torn between patriotism and despair. Universities were emptied of young men, laboratories turned silent. Amid the turmoil, he continued his research, serving as a moral voice for reason and perseverance. Yet tragedy began to touch his personal life. His first wife died young, leaving him with 4 children. Later, one of his sons was killed in battle, and during the Second World War, another was executed for resisting the Nazi regime. Through all this pain, Planck's devotion to science remained unbroken. He believed that the pursuit of truth was sacred, something no war or ideology could corrupt. Even as bombs fell on Berlin, he continued to write, teach, and inspire to his students. He became a symbol of integrity, a man who stood for the purity of knowledge when the world itself was losing its reason. But long before those years of turmoil, his early struggle with blackbody radiation had already shaped his soul. The patience, humility, and endurance required to confront an unsolvable problem had forged in him a strength that would carry him through tragedy. In every line of his notebooks, one can sense not only a scientist at work, but a philosopher searching for harmony. In those early decades, as quantum theory spread and evolved, many of its pioneers would look back to Planck with awe. Einstein called him a man of unfailing intellectual honesty. Niels Bohr, whose own interpretation of quantum mechanics would soon redefine physics, referred to Planck as the father of it all. Yet Planck himself remained modest, sometimes even dismissive of his own fame. He preferred to speak of his discovery as a natural step in the progress of science, not as a revolution. But history would remember it differently. When we imagine those nights in Berlin, the gas lamps flickering, the chalk dust in the air, the long silence after the last equation is written, we can almost feel Planck's quiet battle. He was wrestling not just with numbers, but with reality itself. The blackbody problem was more than a technical question, it was a mirror reflecting humanity's limits. How could something so small, so abstract, hold the key to all matter and energy? And how could one man, sitting alone at his desk, bridge the gap between the visible and the invisible? In later years, Planck often spoke of the spiritual side of science. He saw no conflict between faith and reason, believing that both sought the same truth from different paths. He once said, "Science cannot solve the ultimate mystery of nature, and that is because, in the last analysis, we ourselves are part of nature, and therefore part of the mystery that we are trying to solve." Those words carry the weight of a lifetime spent searching, and perhaps the quiet understanding that some mysteries are meant to remain. As quantum theory matured, Planck's constant, the tiny number that defines the size of a quantum, became one of the cornerstones of physics. It appears in every equation describing the atomic world, from the structure of electrons to the creation of light. It is, in a sense, the signature of Planck's struggle, a mathematical symbol born from persistence, humility, and faith in logic. Yet the irony remains, the man who gave birth to the quantum revolution never fully embraced its most radical implications. By the 1920s and 1930s, younger physicists, Heisenberg, Schrödinger, Dirac, had carried quantum theory into realms Planck could scarcely imagine. The uncertainty principle, wave mechanics, quantum fields, all of these grew from the seed he planted. Planck watched with fascination and discomfort as these new ideas flourished. He admired their brilliance but often expressed skepticism. He remained anchored to the belief that beneath the apparent randomness, there must be an underlying order. In the quiet of his later years, Planck reflected on his long journey. He had lived through empires, wars, revolutions, and yet his most profound battle had been with a single idea. He had learned that sometimes, progress in science does not come from grand ambition, but from stubborn curiosity, from the refusal to look away from a problem that refuses to be solved. The blackbody problem had seemed trivial, a minor crack in the smooth surface of physics. Yet through that crack, Planck glimpsed an entirely new world. Imagine him now, sitting by the window of his study, watching the winter light fade over Berlin. On his desk lies the formula that bears his name, neat and precise, written in the calm hand of a man who never sought glory. Around him, the instruments of his trade, notebooks, compasses, rulers, stand as silent witnesses to decades of thought. Perhaps, in that moment, he feels both pride and melancholy. He has answered the question that haunted him, but in doing so, he has revealed countless others. The mystery of radiation, once so perplexing, has unfolded into the far deeper mystery of the quantum world, a world of uncertainty, probability, and paradox. The beauty of Planck's story lies not only in his discovery but in his humanity. He represents the rare scientist who changes the world without intending to. His struggle reminds us that truth often emerges from persistence, not ambition, from faith in reason, even when reason seems to fail. And it shows that revolutions can begin not with noise and applause, but with silence, patience, and doubt. Before Einstein, before Bohr, before the atomic age, there was Max Planck alone in his study, wrestling with equations that refused to obey the old rules. His mind was a bridge between two centuries, two visions of reality, one rooted in certainty, the other in mystery. And in that fragile space between them, he found the spark that would ignite the quantum world. The story of his early struggle is not merely the tale of a scientist solving a puzzle. It is the story of humanity confronting the limits of its understanding. It is about humility before nature, the willingness to admit that the universe is stranger, deeper, and more beautiful than our logic can grasp. Max Planck's Blackbody problem was, in truth, the universe whispering its first quantum secret to a man who had the patience to listen. Today, every time a laser shines, every time a transistor switches, every time a quantum computer processes a calculation, it carries within it the echo of Planck's perseverance. The constant that bears his name is more than a number. It is a reminder that the path to discovery is often paved with uncertainty and quiet endurance. When we speak of him now, we should remember not only the equations but the man, the sleepless nights, the doubt, the faith in truth, the quiet courage to follow the evidence wherever it led. In that sense, Max Planck was not just the father of quantum theory. He was the embodiment of the scientific spirit itself, humble before mystery, relentless before ignorance, and faithful to the belief that even in the darkest corners of confusion, there is order waiting to be found. And so, long before Einstein illuminated the cosmos with relativity, there was Planck, the forgotten father who first cracked open the door to the quantum realm, who dared to question the completeness of classical thought, and who proved, through patience and persistence, that even the smallest idea can change the course of history. His struggle was not in vain. It was the struggle that gave birth to modern physics, the struggle that turned darkness into light. At the turn of the 20th century, the air in scientific Europe was heavy with certainty. To most physicists, the universe was a clockwork machine, predictable, continuous, elegant. Newton's laws described the motion of every planet and pebble. Maxwell's equations united electricity, magnetism, and light, and thermodynamics governed the dance of heat and energy. It seemed as though the grand symphony of nature had been written and performed to perfection. Yet within that apparent harmony, one small discordant note persisted, the strange riddle of radiation. Max Planck, a man of discipline and restraint, had spent years wrestling with that riddle. His earlier studies of blackbody radiation had led him to a formula that miraculously matched experimental data. But beneath that success lay a disturbing idea, that energy might not flow smoothly, but rather in abrupt jumps. To Planck, this was not a revelation, it was a heresy that threatened to tear apart the very fabric of classical physics. He introduced it reluctantly, almost as a mathematical trick, hoping that time and reason would eventually return him to the safe shores of continuity. But the universe had other intentions. In 1900, when Planck presented his new radiation law, he had no idea that he had planted the seed of a revolution. He derived his equation by assuming that the oscillators, the atomic scale vibrators, responsible for emitting radiation, could only exchange energy in discrete units. Each unit was proportional to the frequency of the vibration, multiplied by a tiny constant that would soon bear his name, h.6626 Ln-Js. It was an unimaginably small number, suggesting that each quantum of energy was almost vanishingly tiny, but even that microscopic discontinuity was enough to change everything. When Planck stood before the German Physical Society that winter evening, the room was filled with colleagues accustomed to elegant certainty. He spoke calmly, methodically, guiding them through his reasoning. The equations flowed neatly across the chalkboard, the derivation seemed flawless. Yet, when he uttered the phrase that energy could be emitted or absorbed only in finite quanta, the words hung in the air like a spark in dry grass. Few in the audience grasped what they had just heard. Fewer still realized that the age of classical physics had ended in that quiet lecture hall. After the talk, the applause was polite, the discussion brief. To many, Planck's presentation was just another step in the long refinement of radiation theory. No one spoke of revolutions. Even Planck himself went home that night uncertain. In his diary, he noted his relief that the results finally matched experiment, but his mind was heavy with doubt. Could nature truly be discontinuous? Could the energy of light really leap in packets rather than flow like a wave? It seemed absurd. Yet the mathematics worked, and mathematics, to Planck, was the language of truth. In the months that followed, he tried to interpret his discovery in a way that would preserve continuity. He explored every possible reinterpretation, hoping that the quanta could be seen merely as a mathematical convenience, not a statement about reality. But each attempt led him back to the same conclusion: there was no escape. The equations demanded discreteness. The universe itself seemed to be quantized. The news of his results spread slowly. The scientific world, still entranced by determinism, paid little attention. For most, Planck's hypothesis was too abstract, too small to matter. But a few young thinkers sensed something deeper. In 1905, Albert Einstein would seize upon Planck's constant to explain the photoelectric effect, revealing that light could behave not just as a wave but as a stream of particles, photons. In that moment, Planck's reluctant assumption transformed from a mathematical patch into a new vision of reality. But before Einstein's leap, there was Planck's inner turmoil. He was not a man given to extremes. His nature was cautious, almost ascetic. He approached science the way a musician approaches a score, with reverence for structure and harmony. To discover that nature itself might play by broken notes disturbed him deeply. He wrote that he had been led by necessity to the idea of energy quanta, as if forced by the data rather than inspired by insight. It was, as he later admitted, an act of desperation, yet also of profound honesty. He could not ignore what the evidence demanded, even when it defied his beliefs. To understand how radical his step was, one must imagine the world he lived in. The very concept of atoms was still controversial. Many physicists considered them mere theoretical fictions, convenient for calculations but not necessarily real. The notion that energy itself could be divided into atomic units seemed fantastical. Yet Planck's constant fit perfectly into the laws of thermodynamics and radiation. It was a key that unlocked the Blackbody spectrum completely, a spectrum that had defied explanation for decades. His equation reproduced every experimental curve, from the dull red glow of a heated metal to the intense blue-white light of the hottest stars. What made Planck's discovery revolutionary was not just the result, but its implications. If energy came in discrete packets, then continuity, the sacred principle of classical mechanics, was an illusion. The universe was granular at its deepest level. The smooth waves of light, the flowing heat, the steady transfer of energy, all were composed of countless tiny jumps too small for human senses to perceive. Reality itself was quantized. In his quiet study, Planck pondered this possibility for years. He tested, recalculated, and rederived his formula using every classical method he knew, hoping to find an alternative explanation. None worked. Eventually, he accepted what his mathematics implied: the quanta were real. With this reluctant acceptance, the door to modern physics swung open. Yet the story of Planck's discovery is not one of sudden genius. It is a story of endurance, patience, and humility before evidence. He did not leap to conclusions, he was pulled, slowly, by the gravity of truth. In a world that celebrated flamboyant innovation, Planck's revolution was almost invisible, a whisper rather than a shout. But sometimes the quietest ideas echo the longest. In the years following 1900, Planck refined his theory further. He introduced the constant H into more general equations, realizing that it could bridge thermodynamics, electromagnetism, and atomic theory. The more he studied it, the more he sensed that H was not merely a parameter, but a fundamental property of the universe. A new natural constant on par with the speed of light, or the gravitational constant. It defined the scale at which the ordinary world dissolved into the quantum. For younger scientists, this was intoxicating. They saw in Planck's constant a gateway to new frontiers. For Planck himself, it remained a riddle. He was fascinated by its precision, by how such a tiny number could govern the vastness of energy and matter. It was as if nature had hidden its secret rhythm in the smallest beat of energy. The quantum had become the new atom, indivisible, mysterious, and profoundly real. As he continued his work in Berlin, Planck's colleagues began to sense the magnitude of what he had done. His lectures drew more attention. Students filled the halls to hear the man who had introduced quanta. Though he still spoke of them with careful restraint, he never claimed to have overturned physics. He spoke instead of refinement, of progress through logic. Yet outside those walls, the world was beginning to change. Einstein's papers on light quanta and relativity, Bohr's atomic model, and later the formulation of quantum mechanics by Heisenberg and Schrödinger would all spring from Planck's single insight. Each new discovery traced its lineage back to that December night in 1900. Planck's constant became the symbol of a new age. An age where certainty dissolved into probability, and reality itself became a field of discrete possibilities. What makes this discovery so extraordinary is how quietly it happened. There was no dramatic experiment, no lightning strike of revelation. It was the result of relentless calculation, a man's refusal to give up on an anomaly. Planck did not intend to change physics. He only wanted to explain why the experimental curve of radiation bent where it did. But in solving that simple problem, he discovered that the universe itself bent differently than anyone had imagined. Even in his later writings, Planck's humility remained striking. He rarely spoke of his discovery in grand terms. When asked about it, he often deflected credit, saying that he had merely followed the logic where it led. But within him, there was quiet pride, not in fame, but in truth. He had glimpsed a structure beneath reality that few could yet comprehend. The revolutionary nature of his discovery went beyond physics. It challenged the philosophical foundations of science itself. For centuries, knowledge had advanced under the belief that the universe was deterministic, that every effect followed from a cause, every motion could be predicted if one only knew the initial conditions. Planck's quanta shattered that vision. At the smallest scales, nature behaved in jumps and probabilities, not in continuous flows. The future could not be calculated exactly, only possibilities could be described. This was a blow not just to physics, but to the very idea of certainty. Planck himself never embraced that interpretation. To him, the quantum was a practical necessity, not a philosophical truth. He continued to believe in an underlying order that human understanding had not yet reached. But his younger contemporaries, Einstein, Bohr, and later Heisenberg, saw in his discovery the beginning of a new worldview. They would take his constant and build upon it until the old universe of cause and effect collapsed into a deeper, stranger reality. Still, all of it, the equations, the debates, the triumphs, began with Planck's quiet act of courage. The willingness to propose that energy came in quanta. It was the most modest revolution imaginable, born not of rebellion but of obedience to evidence. In that moment, science turned a corner it could never turn back from. As the years passed, Planck began to see his discovery reflected in everything around him, in the glow of a heated metal, in the color of the stars, in the structure of atoms. His constant governed them all. What had begun as a desperate hypothesis became the cornerstone of physics. Every new experiment confirmed it. Every new theory relied on it. The quantum had become the heartbeat of the cosmos. Planck's revolutionary discovery was not just about energy. It was about the nature of truth itself. It taught humanity that even the most fundamental laws could break, that certainty was an illusion, and that the universe, at its core, was built from discontinuities, from tiny, indivisible moments of change. The man who had once feared discontinuity came to accept it as the deepest expression of order. In the stillness of his calculations, he had heard the rhythm of creation. The year was 1900, and the air of European science was heavy with certainty. Physicists believed they had nearly completed the grand tapestry of nature. Newton had explained motion, Maxwell had united electricity and magnetism, and thermodynamics had given order to energy and heat. To many, physics was a finished cathedral. But deep within that structure, cracks were forming, cracks that only a quiet, methodical German professor named Max Planck could see. Planck did not look like a revolutionary. He was conservative by nature, loyal to the old laws, a man who trusted logic over imagination. Yet destiny often hides in quiet hearts. For years he had been fascinated by a strange problem: why objects emit light differently at various temperatures. When you heat iron, it glows red, then orange, then white. That change, called Blackbody radiation, was supposed to obey classical physics. But when Planck calculated it using existing laws, something horrifying happened. The energy output shot to infinity at high frequencies. This paradox, later known as the ultraviolet catastrophe, mocked everything physicists believed in. Planck refused to accept chaos. For 6 long years he tried every mathematical trick, every assumption, every possible curve that might fit the experimental data. He worked in silence, sometimes late into the night at the University of Berlin, his papers littered with failed equations. He was not seeking fame. He wanted harmony between theory and observation, between reason and nature. Yet the numbers would not obey. Then, one autumn evening in October 1900, a new idea crept into his mind. It was so strange, so out of character, that he hesitated even to write it down. What if energy is not continuous? What if it comes in small, indivisible packets? He called each packet a quantum of energy, proportional to its frequency by a constant, what we now call Planck's constant, h. That single thought shattered the smooth, infinite world of classical physics. Suddenly, energy was grainy, quantized, limited. Planck derived a new formula using this daring assumption, and to his amazement, the numbers fit perfectly. The experimental curves matched like pieces of a cosmic puzzle. He had found the key that unlocked Blackbody radiation, but he did not yet realize he had also opened the door to a new universe. When he presented his findings on December 14, 1900, to the German Physical Society, few noticed history being made. There were no gasps, no headlines, no applause. It was a quiet meeting in Berlin, another lecture among many. Planck read his paper, explained the constants, and concluded modestly. Yet in that room, the age of quantum physics had begun. Still, Planck himself was uneasy. He did not believe energy quanta were physically real. To him, they were a mathematical trick, a temporary tool to make the theory work. In his heart, he longed to return to the continuous world of Newton and Maxwell. But the equations were relentless. They told a different story, one that would soon echo across the entire scientific world. In the following months, Planck refined his constant and calculated its value with remarkable precision. It was an almost mystical number, tiny beyond imagination, but fundamental to the structure of the universe. This constant linked energy and frequency, light and matter, theory and experiment. It would later appear in every corner of quantum mechanics, from the behavior of atoms to the birth of the cosmos itself. As the new century dawned, physics stood unknowingly on the edge of a revolution. Einstein, Bohr, Schrödinger, and Heisenberg were still students or children when Planck took that leap. He had cracked open reality itself, even if he could not yet see what lay beyond. His act of desperation, as he later called it, would inspire the next generation to explore the strange territory of uncertainty, probability, and duality. But for Planck, the discovery brought as much discomfort as triumph. He could not abandon the belief that nature was orderly, deterministic, and continuous. He wrote letters to colleagues, searching for ways to reinterpret his theory without quanta. Yet every attempt failed. The more precisely he examined his own equations, the more the quanta refused to disappear. It was as if the universe was whispering a truth that Planck's classical mind could not bear to hear. Outside the world of theory, life went on quietly. Planck continued teaching, composing music, and walking the peaceful streets of Berlin. He was a devoted husband and father, a man who balanced scientific rigor with human warmth. But beneath his calm surface, something profound was shifting. He began to realize that he had uncovered a principle deeper than even he could understand. Nature, it seemed, played by rules far stranger than human intuition allowed. In the years that followed, the young and daring Einstein would seize upon Planck's idea and push it further, showing that light itself was made of quanta, photons. Others, like Bohr and de Broglie, would extend the idea to matter, revealing that even particles had a dual nature. Slowly, the scientific world came to accept that the foundations of classical physics had cracked, and through those cracks, a new light was shining. Yet, in every textbook and every experiment that confirmed the quantum, Planck's constant remained the silent signature of his genius. It became the most famous constant since Newton's G, a universal fingerprint of the microscopic world. Whether in the emission of stars or the flicker of an LED, Planck's formula governs the dance of energy and matter. As the 20th century unfolded, entire technologies rose from this revelation: semiconductors, lasers, nuclear power, and eventually quantum computing. The modern world was built upon the idea that energy is quantized, that reality itself is made of discrete steps. Planck had unknowingly rewritten the code of the cosmos. Still, he remained humble, almost detached from his own triumph. "I did not seek to found a new physics," he once wrote. "I only wished to bring order to the chaos." That statement captures the essence of Planck's character. A man driven not by ambition, but by a deep moral duty to truth. He did not chase glory, he sought understanding. Even in his later years, when the world hailed him as the father of quantum theory, Planck continued to see himself as a servant of nature's laws, not their master. He spoke often about the moral dimensions of science, about the need for patience, discipline, and reverence for the unknown. In his view, every equation was not merely a tool but a prayer, a humble attempt to read the mind of God. The simplicity of his discovery is deceptive. It took centuries of observation, generations of minds, and one quiet genius willing to defy intuition to realize that energy is not continuous. The consequences of that realization are still unfolding today, in every quantum experiment, in every flicker of digital light that defines our age. As the story of Planck's discovery closes, one is left with a paradox as deep as the one he faced. The man who believed least in the quantum world gave birth to it. The scientist who clung to classical order became the father of uncertainty. History often works in irony, and in that irony lies beauty. From the glow of a heated metal to the birth of the quantum universe, Planck's journey reminds us that truth does not always roar. It whispers patiently, waiting for someone who listens closely enough to hear. His constant, H, stands as a bridge between the finite and the infinite, a symbol of how one man's perseverance transformed the impossible into the inevitable. And so, the story of Max Planck's quanta is not merely a tale of physics, it is a story of faith, doubt, and discovery, the eternal struggle between what we see and what we cannot yet imagine. It is the moment when humanity realized that the universe, At its core pulses not in smooth waves, but in tiny, sacred beats of energy, each one a quantum, each one a note in the grand symphony of existence. When Max Planck first introduced the idea that energy might come in discrete quanta rather than continuous waves, the world of physics did not erupt in excitement. It froze in disbelief. To the established scientists of 1900, Planck's equation was elegant, but his assumption was outrageous. For centuries, the dream of science had been to find harmony, a smooth, continuous description of nature, from the graceful orbits of planets to the rippling waves of light. And here was Planck, suggesting that nature, at its very heart, was jagged, discontinuous, made of invisible steps instead of flowing curves. It sounded almost heretical. In the early years of the 20th century, Germany stood at the peak of intellectual power. The universities of Berlin, Munich, and Göttingen were temples of classical physics. Men like Hermann von Helmholtz, Ludwig Boltzmann, and Wilhelm Wien had built their careers on the firm foundations of thermodynamics and electromagnetism. They believed that every process in the universe could be explained by continuous mathematics, a world of smooth change and predictable cause. Planck's idea was not merely new, it was a betrayal of that ideal. At first, most of his colleagues simply ignored him. His lecture to the German Physical Society in December 1900 attracted little comment. A few polite nods, a few curious glances, but no one realized that history had just turned a page. To them, Planck's formula was just another mathematical curiosity, a temporary fix to the Blackbody problem, an elegant trick that would soon be replaced by something more respectable. Even Planck himself struggled to believe his own discovery. He was not a man of revolutions, he was a man of order. He had spent his career defending the second law of thermodynamics and upholding the unity of classical physics. Now, against his own instincts, he had been forced to break the very continuity he revered. He described his discovery later as an act of desperation, not of inspiration. That phrase revealed the torment beneath his calm exterior. Over the next few years, Planck's papers received minimal attention. Scientific journals published them, but few discussed them. The great physicists of Europe, Lorentz in Holland, Rayleigh in England, and Poincaré in France, were skeptical. They accepted the mathematical success of his formula, but dismissed the physical meaning of quantized energy. To them, energy could not come in jumps. It was as absurd as saying that temperature changes in steps or that a melody skips over certain notes. Nature, they insisted, was continuous. There were reasons for their caution. Physics, by 1900, had achieved triumphs that seemed eternal. Maxwell's equations had unified electricity, magnetism, and light. Thermodynamics had explained the behavior of gases, engines, and heat. Everything seemed connected, consistent, and certain. The dream of a theory of everything was almost within reach. The idea of discrete quanta threatened to tear that dream apart. If Planck were right, the smooth equations of Maxwell and Newton could no longer describe the smallest scales of nature. The heart of physics would have to be rewritten. In Berlin, Planck's colleagues respected him as a thinker of integrity, but considered his new idea a curiosity, perhaps an error, perhaps a temporary tool. He was 50 years old, a respected professor, not a young radical. Revolution was not in his blood. That made the situation even stranger. How could such a conservative man propose something so outrageous? Some whispered that Planck himself did not understand the implications of his own theory. For a while, it seemed they were right. Planck tried desperately to reinterpret his results in classical terms, to make the quanta disappear. He even wrote letters to friends like Nernst and Rubens, asking whether they could find another explanation for blackbody radiation, one that did not require discrete energy. But no one could. The math was undeniable. Still, the physics establishment refused to bend. When the young Albert Einstein entered the stage in 1905, he saw what others could not. Building on Planck's equation, Einstein proposed that light itself was made of quanta, photons. To him, Planck's idea was not just a mathematical trick, it was the truth about nature. But Einstein's paper was met with the same skepticism, even ridicule. Critics called it absurd, accusing him of trying to resurrect the particle theory of light that Newton himself had abandoned centuries earlier. Planck admired Einstein's brilliance, but could not bring himself to believe that light was made of particles. Ironically, the man who had fathered the quantum world could not yet accept his own child. In the scientific meetings of those years, discussions often grew heated. Old masters defended classical theory with pride, while younger thinkers whispered about new possibilities. The tension was palpable: two generations, two visions of nature colliding. For Planck it was a lonely place. He stood between worlds, too modern for the classical physicists, too cautious for the radicals. He was both pioneer and prisoner of his own discovery. The resistance he faced was not just scientific but philosophical. For centuries, physics had been built upon determinism, the belief that if you knew the position and motion of every particle, you could predict the entire future of the universe. Planck's quanta introduced uncertainty, a flicker of unpredictability at the core of energy itself. To many scientists, that was intolerable. They were not ready to accept a universe ruled by chance or probability. Some of Planck's colleagues accused him, quietly, of undermining the unity of science. Others simply pitied him, thinking he had strayed too far into abstraction. For nearly a decade after his discovery, his theory remained a fringe idea, confined to the margins of discussion. Planck continued his lectures, teaching thermodynamics and electromagnetism as if nothing had changed. Yet deep inside, he knew something had. His struggle was not merely external. It was internal, almost spiritual. He was torn between loyalty to classical law and obedience to experimental truth. Each day he sought refuge in music, playing piano to soothe his restless mind. To him, music and physics were both expressions of harmony. But now, the harmony of the universe seemed broken into discrete, disjointed notes. How could reality itself be quantized? By 1910, the tides began to shift. Experiments by Millikan on the photoelectric effect, and by others on atomic spectra, began to confirm the strange predictions of quantum theory. Slowly, the resistance softened. Planck's formula, once dismissed, began appearing in textbooks and research papers. Yet the old guard remained skeptical, clinging to the belief that quantization was only an illusion. Planck, ever humble, did not fight them. He let evidence speak for itself. Even when recognition came, it was not triumph but relief. When Planck received the Nobel Prize in Physics in 1918 for his discovery of energy quanta, he spoke with gratitude but also with restraint. He reminded the audience that every new truth in science must first pass through 3 stages. It is ridiculed, then violently opposed, and finally accepted as self-evident. He had lived through all 3. In his later years, Planck looked back on those early days of rejection with understanding, not bitterness. He knew that great ideas often seem impossible when they first appear. He even admitted that if someone else had proposed quantized energy before him, he might not have believed it either. That humility defined him more than any discovery. But the story of resistance was not only about physics. It was about the human condition. It showed how even the brightest minds can be prisoners of their own success, how the comfort of established truth blinds us to new realities. Planck's struggle revealed the price of progress: isolation, doubt, and patience. He endured all 3 without anger, holding fast to the belief that truth, however strange, would eventually prevail. By the 1920s, when quantum mechanics finally took shape through the work of Heisenberg, Schrödinger, and Dirac, the world had caught up with Planck's vision. Yet even then, debates raged on. Einstein himself rebelled against the randomness implied by quantum theory, declaring that God does not play dice. Planck, older and wiser, simply smiled. He knew that the universe was not obligated to fit human comfort. It was obligated only to be true. Looking back, it is clear that Planck's greatest challenge was not solving the equations of blackbody radiation, but surviving the storm of disbelief that followed. His quiet persistence in the face of skepticism became a model for scientific courage, not the flamboyant kind that shouts for attention, but the kind that endures in silence. When the history of modern physics is told, the names of Bohr, Einstein, and Schrödinger shine brightly. Yet none of their achievements would have been possible without the lonely determination of Max Planck, who faced a world that doubted him and stood firm. He once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it." Those words were not cynical. They were honest. He had seen the truth struggle, suffer, and finally survive. As the early decades of the 20th century faded into history, the very scientists who had dismissed Planck's theory began teaching it to their students. The once absurd idea of quanta became the foundation of atomic and molecular physics. The constant that bore his name, h, became the heartbeat of a new universe, one that danced to rhythms no one had imagined before 1900. But the memory of that early resistance never left him. It became a quiet reminder that every discovery worth making must walk through the valley of doubt. Max Planck's journey was not only a scientific triumph, it was a testament to the power of patience, humility, and faith in the language of nature. As the years after 1900 stretched on, the echo of Planck's strange proposal spread quietly through the corridors of European science, yet it carried a peculiar stillness. There was no revolution in the streets of physics, only cautious whispers in university halls. Professors mentioned his work with polite curiosity, like a rumor one doesn't wish to believe, but cannot quite dismiss. Journals referenced his equation, but rarely the quantum that gave it life. For Planck, it was a lonely triumph, one wrapped in silence rather than applause. In the grand lecture halls of Berlin, he continued his daily routines, teaching, calculating, composing music on his piano in the evenings. To his students, he appeared calm, dignified, unshaken, but privately, he was aware that his idea stood at the edge of exile. Few colleagues would discuss it seriously, and those who did often tried to reinterpret it to preserve the smooth fabric of classical physics. In their eyes, quantization was an ugly patch on a beautiful theory. Planck, the perfectionist, understood their discomfort because he shared it. Yet he could not turn away from the evidence his own equations revealed. Every generation of science has its heretics, people who disturb the comfort of certainty. Planck had become one unwillingly. What tormented him most was not rejection, but misunderstanding. When critics accused him of breaking with classical continuity, he protested that he had done no such thing. He saw the quantum not as a rebellion against tradition, but as an adjustment within it. But history has its own irony. Sometimes the smallest adjustment can open the widest abyss. Across the continent, other physicists continued their search for a purely classical explanation of blackbody radiation. In England, Lord Rayleigh and Sir James Jeans published alternative models that worked at low frequencies but failed catastrophically at high ones. Each failure tightened the circle around Planck's formula. Still, few dared to confront what it implied. The notion that nature might operate in discrete packets seemed to violate the very soul of physics. Meanwhile, a young Swiss patent clerk named Albert Einstein was quietly absorbing Planck's papers. In 1905, he would transform them into something new, claiming that light itself consisted of quanta, later called photons. For Planck, this was both thrilling and unsettling. He admired Einstein's courage, but resisted his interpretation. To him, quantization applied to the exchange of energy between matter and radiation, not to light itself. He still clung to the belief that waves were continuous. The irony deepened. The student who believed more than the master became the torchbearer of his revolution. As Einstein's ideas spread, so did the controversy. Experimentalists struggled to confirm or refute the photon theory. Some, like Robert Millikan, set out to disprove Einstein, only to find their experiments confirming him. Yet acceptance came slowly, and Planck watched this with mixed emotions. He saw his constant, h, appearing in new contexts, photoelectric experiments, atomic spectra, but he remained cautious, unwilling to surrender the continuous vision of nature. His mind, trained in the discipline of 19th-century order, could not easily embrace the chaos of probability that was beginning to surface. Within scientific circles, resistance hardened before it softened. At conferences in the first decade of the century, older physicists shook their heads at the very mention of quanta. They called it unphysical, artificial, even metaphysical nonsense. The atmosphere was one of polite hostility. Younger minds, however, felt the stir of something new. They were restless in the old frameworks, drawn by the mystery of atoms and radiation that classical theory could not fully explain. Planck became a bridge between these generations. He defended Einstein's early papers when others attacked them, not because he fully agreed, but because he valued honest inquiry above conformity. In letters to colleagues, he argued that scientific truth is not determined by majority vote, but by consistency with nature's laws. Those words, calm and simple, revealed his quiet defiance. He would not shout, but he would not yield to ignorance either. Still, doubt was not confined to others, it lived in him too. He often revisited his own derivations, searching for a way to eliminate the discontinuity. Each attempt ended where it began, with H, stubborn and irreducible. It was as if the universe itself refused to speak in the smooth language of human expectation. He once wrote in his notebook that, "A law that arises from desperation may yet conceal the deeper order of nature." That phrase captures his state of mind, torn between the yearning for order and the recognition of mystery. Outside the lecture halls, the world was changing. Industry, technology, and war reshaped Europe. Physics was moving from chalkboards to laboratories filled with glowing tubes and electric sparks. New instruments probed the invisible realm of the atom, revealing patterns that screamed for a new theory. Spectral lines appeared where continuous light should have been. Electrons behaved like waves, and waves acted like particles. Each discovery whispered the same truth Planck had glimpsed years earlier. But the human mind resists change as fiercely as nature obeys it. Even as evidence mounted, many clung to the comfort of continuity. Einstein himself, though once a champion of the quantum, began to question its implications when Heisenberg and Bohr pushed it into a theory of uncertainty. Planck, now older, watched these debates with the wary wisdom of one who had already walked through disbelief. He no longer fought the tide, he simply observed, knowing that truth unfolds at its own pace. In those later years, he often reflected on the peculiar path of his idea, from neglect to confusion to reluctant acceptance. When young scientists visited him in Berlin, he would speak softly about patience. Science progresses one funeral at a time, he told them with a gentle smile, not in cynicism but in recognition of human nature. Old beliefs rarely die by persuasion, they fade as new minds grow up unburdened by them. The resistance he faced had shaped him more than success ever could. It taught him humility, the knowledge that even a correct idea can be invisible until the world is ready to see it. It also taught him compassion for the next generation of rebels. When Niels Bohr introduced his atomic model, or when Heisenberg spoke of uncertainty, Planck listened rather than judged. He understood what it meant to be doubted, to carry a truth that feels heavier than the world's acceptance. There is a quiet heroism in persistence without recognition. Planck embodied that. While others sought fame or followers, he sought coherence. When ridicule came, he endured it with the calm of a man who trusted the slow justice of evidence. His belief in reason was almost spiritual. "Truth never triumphs," he said once, "it just doesn't die." Those words became a guiding light for generations of physicists who would later face their own storms of skepticism. Eventually, the very constant that had once been ignored became the cornerstone of modern physics. Planck's H appeared in every quantum equation, from Schrödinger's wave mechanics to Heisenberg's matrix theory. What had begun as an act of desperation turned into the alphabet of the microscopic universe. The irony could not have been greater. The man who introduced the idea most reluctantly became its eternal symbol. By the time he received the Nobel Prize, The scientific resistance had mostly softened into respect, yet even then, Planck's acceptance speech was not one of triumph but of gratitude. He thanked those who had challenged him, saying that doubt is the lifeblood of science, for without it, truth becomes dogma. That humility set him apart from many of his successors, whose revolutions were louder but not always wiser. In his twilight years, as Europe descended once again into turmoil, Planck carried with him the scars of skepticism and the serenity of vindication. He had lived long enough to see quantum theory blossom into a forest of discoveries, each branch bearing fruit beyond his imagination. Yet the memory of those early years, when his peers dismissed him, never faded. It reminded him that progress is not a straight path, but a struggle between curiosity and comfort. When younger scientists asked him how he had endured the long winters of disbelief, he would tell them that conviction must never depend on applause. The applause comes late, if at all. What matters is fidelity to the evidence, however uncomfortable it makes us. In those words lay the moral of his life story, that truth requires courage not in shouting but in waiting. Max Planck's journey through skepticism became one of the most profound lessons in the history of science. It revealed that revolutions are not born in chaos but in quiet persistence, that the hardest barrier to new knowledge is not ignorance but certainty, and that the path of discovery often begins with isolation. When the world laughed at his quanta, he did not argue, he calculated. When it doubted him, he refined his constant. When it ignored him, he simply continued to teach. In the end, that steady patience changed the world more deeply than any fiery manifesto could have done. Now, more than a century later, the very technologies that define civilization — computers, lasers, satellites, medical imaging — owe their existence to the principle once mocked in Berlin's lecture halls. Every photon that carries data across the globe, every quantum bit that stores information, is a silent tribute to the man who faced disbelief with dignity. The resistance has long vanished, but the echo of his perseverance endures. There is a quiet scene that captures the spirit of his struggle. In his later years, during a lecture at the Prussian Academy, a student asked him whether he regretted proposing the quantum theory, given how much it had unsettled physics. Planck paused for a long moment before answering. Then he smiled and said, "No, for nature compelled it. I only listened." That answer, simple and profound, contained the essence of science itself. The humility to listen when the universe speaks in unfamiliar tones. The skepticism he faced was not a tragedy but a necessary crucible. Without resistance, ideas remain fragile. They gain strength only when tested by disbelief. Planck's theory survived because it was true, and truth, though delayed, does not perish. The world eventually caught up with him, as it always does with those who see further than the present allows. When he passed away in 1947, the age of quantum physics was in full bloom. The same scientific community that once doubted him now built entire laboratories and industries upon his constant. Yet among the monuments and accolades, what endures most is the image of a quiet man at his desk, wrestling with equations that defied his own expectations, guided by nothing but integrity and patience. His story is not just a chapter in the history of physics, it is a mirror for all human inquiry. Every field, every generation, faces its Planck moment, the instant when reality demands that we abandon comfort for truth. In that moment, resistance always rises, but so does discovery. Planck's life reminds us that the two are inseparable, that skepticism is not the enemy of progress but its most faithful companion. So, as the modern world continues to unravel deeper mysteries, the quantum universe, the multiverse, the nature of consciousness, the spirit of Max Planck endures. His name, once whispered with doubt, is now spoken with reverence. Yet the moral of his struggle remains timeless, that truth is not measured by acceptance but by endurance, that every great idea must survive its season of disbelief before it becomes self-evident, and that the greatest revolutions begin, as his did, in the silence of one mind listening carefully to the voice of nature. The First World War had just ended, and Europe lay in ruins. Physically, morally and intellectually. The certainties that once guided civilization had been shattered. In this fragile new era, Max Planck stood as one of the last old guardians of science, carrying the torch of reason through the storm of history. Though he had opened the door to the quantum world, he was still trying to understand the deeper meaning of what he had unleashed. He was no longer a young man chasing equations, but an elder statesman of physics, a witness to both the triumphs and tragedies of his age. In the early 1920s, the world of physics was in turmoil again, but this time not from war. It was the revolution that Planck had unknowingly started. Einstein had already shown that light behaves as particles, Niels Bohr had built his quantum atom, and now new minds, Heisenberg, Schrödinger, and Dirac, were reimagining reality itself. The equations they wrote defied common sense. They spoke of probabilities instead of certainties, of electrons that existed in many places at once, of energy that could only be understood through observation. The universe had become a theater of paradoxes. Planck watched this new generation with mixed emotions. He admired their courage, their brilliance, their refusal to be limited by old beliefs. Yet he could not fully accept their vision. To him, nature was still governed by laws, not by chance. He respected Heisenberg's uncertainty principle and Schrödinger's wave theory, but he longed for the order that had once defined physics. In his lectures, he spoke of balance, between experiment and theory, between innovation and respect for the past. He was proud to see his discovery inspire others, but he also felt like a father watching his children tear down his house to build a new one. Outside the laboratory, the world around him was darkening again. Germany was struggling with political chaos and the rise of extremism. Planck, who valued truth and ethics above all, tried to keep science free from politics, but the world would not let him. In 1933, Adolf Hitler rose to power, and the freedom of thought that had defined German science was attacked. Jewish scientists were dismissed from universities. Many of Planck's closest colleagues and friends, Einstein among them, were forced to flee. Planck, old and wary, tried to intervene, writing letters, appealing to reason, pleading for fairness. But reason had lost its voice in a world of hate. Despite the pressure, Planck refused to abandon his moral compass. He believed that science belonged to humanity, not to nations or ideologies. He continued his research quietly, protecting young physicists where he could, speaking softly but firmly for the principles of truth and integrity. When asked why he stayed in Germany, he said, "A captain does not desert his ship in a storm." His words reflected the same discipline that had guided him through his life, faith in duty. Even when hope seemed lost, tragedy struck his personal life as brutally as the world around him. His home was destroyed in Allied bombings. Worse still, his son Erwin was executed by the Nazi regime in 1945 for participating in a plot against Hitler. Planck, then in his late 80s, was devastated. The man who had given humanity a new vision of the universe had lost almost everything: his family, his home, his nation's honor. Yet even in grief, he did not let bitterness consume him. He turned once again to science, to philosophy, and to the quiet contemplation of nature's eternal order. In the final years of his life, Planck spoke often about faith, not religious dogma, but faith in the rational structure of the cosmos. He believed that every discovery brought humanity closer to the divine logic behind creation. "Science cannot solve the ultimate mystery of nature," he once said, "because we ourselves are part of that mystery." These words captured his humility, his awareness that even the greatest mind can only glimpse a fragment of truth. When Max Planck died in 1947, he left behind more than equations. He left a legacy of perseverance, of intellectual honesty, of moral courage. The constant that bears his name became the foundation of modern physics, but his true gift to the world was his example, that even in times of darkness, the pursuit of truth must never stop. His story is a quiet reminder that revolutions in thought are not born from noise and ambition, but from patience, discipline, and faith. Before Einstein's relativity and before the dazzling paradoxes of quantum mechanics, there was Planck, a man who sought only to explain a curve of light and ended up redefining reality itself. In his calm and unyielding way, he showed that even the smallest idea, when pursued with honesty, can change the course of history. The twilight of Max Planck's life was a period of reflection, an age when the man who had unknowingly ignited the quantum revolution stood at the edge of time, watching his discovery transform the world in ways he had never imagined. The 20th century was roaring forward, powered by the very physics that had begun in his quiet Berlin study decades earlier. Radios X-rays, nuclear power, and the dawn of atomic theory all traced their roots back to his daring idea that energy came in quanta. Yet, as the scientific world celebrated its progress, Planck himself looked upon it with a deeper, more philosophical gaze. He had never sought fame, and even as his name was etched into textbooks and laboratories, he remained the humble thinker who saw science as a path to truth, not glory. By the mid-1940s, the implications of quantum theory had reached far beyond physics. Einstein's relativity had reshaped space and time, while Planck's quantum principle had revealed that even energy itself came in discrete steps. Together, they formed the twin pillars of modern science, defining everything from the atom to the cosmos. But Planck, always thoughtful and reserved, viewed these advances not as conquests but as revelations, glimpses into the deeper harmony of nature. He often spoke of the symphony of the universe, a phrase that revealed his lifelong connection between music and science. For him, every equation was a melody, every discovery a chord in the eternal music of creation. Even as he aged, Planck continued to write and lecture, his voice calm and deliberate. He spoke not of triumph, but of duty. To him, science was a sacred calling, an act of faith in the rational beauty of the cosmos. He reminded young physicists that knowledge without ethics was dangerous, that the pursuit of understanding must always serve humanity, not destroy it. In a century soon to witness the atomic bomb, born indirectly from the very principles he helped discover, his words were prophetic. He warned that power without wisdom could turn science into tragedy. Yet he never lost faith in the human spirit or in the idea that truth would ultimately lead mankind toward light, not darkness. In his later reflections, Planck described how science and spirituality were not enemies but companions. He believed that every scientific truth carried within it a spark of the divine. For him, the deeper one went into physics, the closer one came to God, not as a figure of myth, but as the ultimate intelligence behind the universe's order. This view did not make him a preacher, but a philosopher of reality. He saw faith not as blind belief, but as the courage to trust that nature's mysteries could be understood. "There is no matter as such," he once said. "All matter originates and exists only by virtue of a force, and we must assume behind this force the existence of a conscious mind." These words, spoken by a man of equations and constants, revealed the soul of a seeker who found wonder where others found mere data. Planck's influence did not end with his death. Generations of physicists carried his ideas into new realms: quantum mechanics, quantum field theory, and eventually the birth of quantum computing and cosmology. Each discovery built upon the foundation he laid, turning his once desperate hypothesis into the bedrock of modern science. And yet, beyond the mathematics, his legacy was moral. He showed that true science is not a race for fame, but a lifelong devotion to truth, that real breakthroughs come not from chaos, but from patience and humility. As the modern world looks back at the story of quantum theory, the spotlight often falls on Einstein, Bohr, or Schrödinger. But behind them all stands the quiet figure of Max Planck, the man who asked a simple question about light and ended up changing reality itself. His life was not marked by grand gestures, but by unwavering discipline, by a belief that reason and morality could coexist even in times of darkness. He endured war, loss, and grief, yet he never surrendered his faith in order or beauty. In the end, Planck's legacy is not just in physics, it is in the spirit of inquiry he embodied. He reminds us that discovery begins with curiosity, survives through persistence, and is guided by conscience. He teaches that even when the world descends into chaos, one mind seeking truth can light a path that leads generations forward. The forgotten father of quantum theory left behind not just a constant, but a lesson for humanity that the greatest revolutions begin not in noise, but in silence, not with destruction, but with the quiet courage to question what everyone else takes for granted. His life remains proof that one idea, born in solitude, nurtured in faith, and tested by time, can transform the destiny of science and the meaning of existence itself. By the time the echoes of the Second World War had faded, Max Planck's name had already become immortal, though his journey had never been one of self-celebration. He was gone, yet his constant lived on in every equation, every photon, every scientific truth that followed. The quiet man from Kiel had reshaped human understanding of the universe, and the generations that came after him built entire worlds upon the foundation he had laid. But the story of Planck's legacy was not just one of physics. It was a story of human endurance, of how a single mind can redefine reality and still remain humble before its vastness. The 20th century began with Planck's discovery and unfolded as a testament to its power. His simple idea, that energy comes in discrete packets, evolved into a principle that governed everything from the smallest particle to the farthest galaxy. What began as an attempt to explain blackbody radiation became the very language of the cosmos. Through Planck's constant, the universe revealed its code, a rhythm of energy that pulsed through atoms, stars, and even the fabric of space-time. Einstein's relativity would describe the grand architecture of the cosmos, but it was Planck's quantum that revealed the flickering heartbeat within it. Physicists soon realized that nothing in nature was truly continuous. Light, once thought to be a smooth wave, behaved like a shower of particles. Matter itself seemed to blur into probability, into a realm where certainty dissolved and only possibility remained. The strange, beautiful chaos of the quantum world stood in contrast to the deterministic order Planck had once believed in. Yet even as his successors, Bohr, Heisenberg, and Schrödinger, pushed deeper into this mysterious reality, they all paid silent tribute to the man who had opened the first crack in the wall of classical thought. Without Planck's courage to question the obvious, the entire edifice of modern physics would never have existed. In universities and laboratories across the world, Planck's constant became a sacred symbol, a reminder that even the smallest number could hold infinite meaning. It appeared in the formulas of atomic spectra, in the energy of electrons, in the birth of stars, and in the faint afterglow of the Big Bang. Every time a photon strikes a sensor, every time an atom emits light, it whispers his name. The digital world, too, computers, lasers, and quantum devices, owes its existence to his vision. The modern age, with all its brilliance and complexity, is built upon the quiet logic of Planck's discovery. But beyond science, Planck's legacy carried a message about humanity itself. He lived through the most turbulent eras in modern history: 2 world wars, the rise and fall of empires, and the moral collapse of his nation. Yet he never surrendered his belief in truth, reason, and the moral duty of the scientist. In a time when many bowed to power, Planck stood for integrity. He spoke softly but firmly about the eternal connection between science and ethics, reminding future generations that knowledge without conscience is a danger to all. His resilience became an example of how intellect and morality must walk hand in hand. To the very end, he believed that nature was not random chaos but divine order disguised in mystery. He saw in every formula the reflection of a higher intelligence. His words, written near the close of his life, still resonate like a quiet prayer. Science progresses not by refuting faith, but by deepening it. He did not mean faith in religion, but faith in the harmony of creation, in the belief that beneath all uncertainty lies a pattern waiting to be revealed. For him, physics was a path to understanding existence itself, a dialogue between the human mind and the cosmic order it seeks to comprehend. When people today speak of quantum theory, they often think of its strangeness, its paradoxes, its defiance of common sense. But for Planck, It was never about strangeness. It was about truth. He did not set out to shock the world, only to explain it faithfully. That is what makes his story timeless. He discovered the quantum not through rebellion, but through obedience to nature's laws. And in that obedience, he transcended them. Planck's life reminds us that revolution can be born in humility, that progress often begins in patience, and that the true measure of greatness is not noise but endurance. His name might not be spoken as often as Einstein's, but his influence lives in every corner of modern thought. Each quantum of energy that lights the world carries his silent legacy. In the grand story of human discovery, Max Planck remains a symbol of how the pursuit of truth, guided by integrity and faith, can transform not only science but the human spirit. He proved that one act of courage and thought can ripple through centuries, changing how humanity perceives reality itself. Long after his passing, his light continues to shine, not as a blaze of fame but as a steady, eternal flame illuminating the path for all who seek to understand the universe. As the story of Max Planck reaches its quiet conclusion, it becomes clear that his true achievement was not only the discovery of the quantum, but the transformation of how humanity perceives truth itself. His life stands as a bridge between two worlds, the world of classical certainty and the world of quantum mystery. Before him, physics believed that the universe was smooth, predictable, and absolute. After him, it became a place of probabilities, discontinuities, and hidden patterns. He did not just change equations, he changed the very questions that science dared to ask. Yet for all his revolutionary impact, Planck remained a man of extraordinary humility, never seeking to be remembered as a hero, only as a servant of truth. In his later reflections, Planck often said that science advances not by sudden leaps, but by the quiet persistence of those who refuse to give up. He was the embodiment of that belief. His discovery did not come from a flash of genius or a dramatic experiment. It was born from years of silent struggle with mathematics and nature, from a mind too honest to accept what did not fit. He called it, or an act of desperation. Yet it became the cornerstone of modern thought. That humility is what makes his legacy eternal. He taught that the greatest revolutions are not loud, but patient. The generations that followed him, Einstein, Bohr, Heisenberg, Schrödinger, Dirac, each took the spark he lit and turned it into a fire that illuminated the deepest mysteries of the universe. Yet even they acknowledged that without Planck, there would have been no quantum theory, no atomic physics, no understanding of how energy, matter, and light dance together in the cosmic order. Every discovery that shaped the modern world, from nuclear energy to quantum computing, flows from the small, careful step that Planck took in 1900. He may not have lived to see the quantum age in its full glory, but it was his hand that opened its door. In the decades after his death, the world came to realize that Planck's constant was not just a number. It was a boundary between the human scale and the cosmic scale, a key that unlocked the hidden structure of existence. It revealed that the universe is not infinitely divisible, that nature itself operates in rhythms and pulses, that even light and energy move in discrete steps. Through that constant, humanity began to glimpse the unity between the physical and the philosophical, between matter and meaning. Planck had, perhaps unknowingly, given birth to a new way of thinking, not just about the universe, but about knowledge itself. As quantum theory matured, it brought with it strange truths that still challenge the imagination, particles that behave like waves, realities that change when observed, probabilities that define existence. These ideas may have startled the world, but they all trace their lineage back to Planck's simple, profound realization. The mystery that began with his study of blackbody radiation evolved into the grand tapestry of modern physics, a world where uncertainty and beauty coexist, and where the boundaries between science and philosophy blur. Yet even as physics advanced into realms of abstraction, Planck's voice remained a moral compass for those who followed. He reminded scientists that every discovery carries responsibility, that understanding the laws of nature also means respecting them. He warned that knowledge without conscience could destroy the very civilization it was meant to elevate. His words echo more powerfully today than ever before, in an age where human technology wields immense power over both the planet and the future. Planck's wisdom endures as a guide, a reminder that true science is not only about knowing, but about caring. Toward the end of his life, Planck spoke often of faith, not in dogma, but in the fundamental order of existence. To him, the pursuit of science was an act of reverence, a dialogue with the mind of creation. He believed that every truth discovered by science brought humanity closer to understanding the divine intelligence that shapes the universe. "Wherever we look," he once said, "we find order, beauty, and harmony. That is the essence of all existence." These were not the words of a man lost in theory, but of one who had seen through the equations into the soul of nature itself. Today, Max Planck's name lives quietly in the background of every technological miracle. The laser beams that cut steel, the atomic clocks that guide satellites, the quantum algorithms that promise a new future. His constant etch defines the very limits of knowledge, standing as a silent reminder of his vision. But his deeper legacy lies beyond numbers and inventions. It lives in the spirit of inquiry he embodied, the courage to question, the discipline to persevere, and the humility to serve truth without pride. Planck's journey from classical physics to quantum revelation mirrors humanity's own journey from certainty to wonder. He began by seeking order and ended by uncovering mystery, showing that knowledge does not end answers, it begins them. In the end, his life became a lesson about the nature of discovery itself, that the greatest truths are often found not in the grand declarations of power, but in the quiet pursuit of understanding, not in the noise of fame, but in the stillness of thought. The world may remember Einstein's relativity or Bohr's atom, but it was Planck who lit the first candle in the darkness, revealing that even the smallest measure of energy contains the secret of the universe. His story is a testament to how one man's patience can change eternity. And so, as science continues to unravel the mysteries of existence, the echo of Planck's insight remains, timeless and profound, reminding us that before light, there was darkness, and before Einstein, there was Planck, the forgotten father of quantum theory, whose quiet brilliance reshaped reality itself.